Hello chemists, this is Miss Placino and you are watching Screencast 5.5 on predicting the products of double replacement reactions. Without question, this is the most challenging lesson of the entire unit. In order to properly predict products, you have to understand how the reactants are going to break apart, what ions are going to form, how to recombine those ions, how to use the charges of the ions to predict the formulas of the compounds that will form. You then have to figure out which of those two products is going to be solid, and finally get the equation balanced. So there are a whole lot of steps to properly predicting the products of a double replacement reaction. I'm going to skip over the do now because we're going to address this question later, and I don't want this to be too long of a lesson. All right, in our double replacement reactions, we usually start off with aqueous reactants. Just as a reminder, in order to make something aqueous, you take a solid, you're going to dissolve it in water, and you're going to form a homogeneous mixture, also known as a solution. So we've got our solid, dissolve it, turns it into a solution. When you dissolve an ionic compound in water, you make something aqueous. Something interesting happens with the ions themselves. So I've got a video to show you about the dissolution or the dissociation of sodium chloride in water. Oops, there we go. So we've got sodium chloride in water. And we know that water molecules are like little magnets. They've got poles. So they're going to be able to interact with the positively and negatively charged ions present in sodium chloride and essentially start to rip it apart. If you notice, whether it's a positive ion or a negative ion dictates what side of the water molecule is going to be attracted. Pause that for a second. That's going to be attracted to the ion. So the chloride ion is negatively charged, and you've got the positively charged hydrogens from the water molecule pointed at it, which makes sense because opposite charges attract. For the sodium ion, that's going to be positively charged. We know in a water molecule, excuse me, the oxygen side of the molecule has a slightly negative charge, so it's going to be attracted to the positive side. But the key really to take away from this is that when you take an ionic compound and you dissolve it in water, it breaks up into ions. These ions are going to be free to react with other ions, possibly producing a precipitate. The first step to predicting products is being able to break apart the reactant molecules. This is called dissociation. So when a soluble ionic compound is dissolved into water, it dissociates, which is just kind of a fancy word for breaks apart into ions. So if we take a look at something like CaCl2, calcium chloride is soluble in water. When I dissolve it in water, it's going to produce calcium ions and chloride ions. What I have to figure out is what is the charge going to be of my calcium ion and my chloride ion. I can use the reverse crisscross method, I can use the reference table, and I can get this figured out. I know that calcium must have a charge of 2+ because chlorine has a subscript of 2. And I know the chloride must have a charge of 1- because calcium has a subscript of 1. Nothing's written there, so it's implied that it's a 1. I can double check that against the reference table and make sure that this isn't a case where things just kind of reduce down into lowest terms. Sure enough, I come up with calcium 2+ and chloride -. I need to make sure that I'm balanced. I've got 1 calcium ion as a reactant, 1 as a product. I've got 2 chloride ions as reactants with the coefficient of 2. I now have 2 calcium ions as my products as well. So both of these are going to be aqueous, AQ, dissolved in water. So we're just going to have calcium and chloride ions floating around in the solution. Don't forget, and we've kind of just talked about this, the subscript of the anion becomes the charge of the cation and vice versa. Just be careful and make sure that things, and when I say things, I mean subscripts, haven't been reduced down to lowest terms. Cross-reference things with your reference table, specifically the periodic table. Let's try some on your own. So pause the video, try these out, see if you can predict what the charge of the ions that form will be and how many of each ion are needed. So we'll make the assumption that all of these ions are going to dissolve in water. When aluminum oxide dissolves in water, we'll form aluminum and oxide ions. Aluminum has a charge of 3+, oxide has a charge of 2-. We need 2 aluminum and 3 oxides to get balanced. Magnesium bromide. Mg2 plus 2 Br minus. And sodium phosphate, don't be fooled here by the 4 from the phosphate. This is not Na4 plus PO3 minus. Phosphate is polyatomic. We have 3 Na plus ions, and then we have only one phosphate, PO4 3 minus ion. This is the first step. You've got to be able to take your reactants and break them up into ions. In order to figure out if something's going to be soluble in water or not, this is called determining its solubility. So soluble means able to dissolve in water. So something like salt is soluble in water. Insoluble is unable to dissolve in water. So we're going to be forming precipitates as a result of double replacement reactions, and the precipitate is a combination of ions that is just not able to be dissolved. We also end up with something called slightly soluble, which is somewhere in between soluble and insoluble. In AP Chemistry, you'll start putting numbers to the solubilities, and it'll be a little bit less vague, but a lot of times slightly soluble, you can just think of it as not a whole lot of that solid can dissolve in water. It would be a lower concentration. And if it's slightly soluble, sometimes we will see it as a precipitate, again, dependent upon the concentration. You've got table F to help you with solubility, and here's how you're going to use this chart. So on the left-hand side, we have ions that form soluble compounds. Oops, erase that. Soluble compounds. And soluble means able to dissolve in water. So usually compounds that have group 1 ions, ammonium, nitrates, acetates, so on and so forth, they are going to dissolve. The exceptions are insoluble. So there doesn't appear to be any exceptions when you have a group 1 ion as the cation, and it doesn't really matter what the anion is, there are no exceptions. That's going to be a soluble ion. You can see a lot of them have no exceptions, hence it's blank. When you get down to the halides and the sulfates, we do see some exceptions. So generally speaking, halides, so that's your group 7, the halogens, we call them the halides when they're ions, are soluble. There are exceptions to that. If you take a halide and you combine it with Ag+, Pb2+, or Hg2 2+, you get an insoluble compound. So something like silver chloride is going to be insoluble. Even though chlorides are usually soluble, silver is an exception. Same thing with sulfates. Sulfates are usually soluble compounds. We have some exceptions. When you combine sulfate with any of these ions listed, you're going to produce an insoluble compound that will not dissolve in water. On the other side of the chart, we have ions that form insoluble compounds. So these are generally ions that are going to form compounds that do not dissolve in water. Carbonates, chromates, phosphates, sulfides, hydroxides tend not to dissolve in water, unless there are exceptions, are slightly soluble. So for example, carbonates tend not to dissolve in water unless you combine them with a group 1 ion. So lithium, sodium, potassium, so on and so forth, or ammonium. See that group 1 and ammonium tend to be exceptions everywhere. There are other ones like hydroxides, usually insoluble. In addition to group 1, we can see that when it forms a compound with calcium, barium, or strontium, we also get a slightly soluble compound. So this is how you're going to use the table. We're going to use this to figure out whether or not the reactants actually can be aqueous, and then when we get to the products, which of those two products will be our precipitate. So now we've got all those ions floating around in solution, and when we recombine ions, we can end up with a compound that will not dissolve. So a precipitate may form. Let's say, for example, you end up with silver plus and sulfide ions, sulfur 2- in solution. When silver and sulfide react, they're going to form an insoluble compound. Your job is to predict the product. And I just do that by using the crisscross method. I have Ag with a charge of 1+. I've got sulfide with a charge of 2-. We've done this before with predicting products. We're going to produce Ag2S, silver sulfide, which is insoluble. So again, crisscross those charges to form the subscripts. If the product is soluble, no reaction occurs. So that just means that they will stay as ions. But if you use that's table F in your reference table, silver ions plus sulfide ions will give you an insoluble product. Let's go ahead and try some practice problems. So predict the precipitate that will form. Figure out the formula of the compound that you're going to make. And I'll tell you right off the bat, they are all insoluble. So just focus on predicting the products and not looking at the solubility rules. Okay, lead 2 plus iodine minus. That's going to make PbI2. If I want to get that balanced, I'm going to put a coefficient of 2 in front of iodine, or I should say the iodide ion. And number 2, you've got barium 2 plus, sulfate 2 minus. So our charges, we can crisscross them. They're going to cancel out because we have to express it in lowest terms, and we get BaSO4, another solid. Chromium and hydroxide, same thing. Let's crisscross them. We know that technically this is a 1. We get CrOH in parentheses 3. Make sure you're not forgetting the parentheses around the hydroxide. So let's start trying to put all of this together. In a double replacement reaction, we're going to dissociate or break apart the reactants, recombine the ions, a cation with an anion, and that's going to form our products. So let's look at a problem together. We have lead 2 nitrate reacting with potassium iodide. Both of these compounds are soluble in water, so when we dissolve them, they're going to be aqueous. Step 1 is to dissociate or break apart the reactants into their ions. So a lot of times I'll just draw little arrows. I know that I'm going to make lead ions, nitrate ions, and I know that I'll make potassium ions and iodide ions. The tricky part is trying to figure out what the charge of these ions are. But we've already done this. We can use, it's essentially the reverse crisscross method. We can take the subscript, make it a charge. We know that's a 1 for lead. We can make that the charge of nitrate. Double check your reference table, make sure the things have not been reduced down. So we end up with lead 2 plus and nitrate minus. Potassium and iodide, I don't see subscripts anywhere there. I know potassium is a group 1 metal, so it's going to form an ion with a +1 charge. I know iodine is a group 17 nonmetal, so when it completes its octet, it'll gain an electron and form I-. And now I've got all of my, or I should say both of my reactants dissociated. Up next, I have to recombine ions. I know that a cation is going to react with an anion, so it's not going to just react with the same anion it already has. I'm going to pair it up with the opposite anion. We'll do the same thing there. All right, I know how they're going to recombine. Potassium will react with nitrate, lead will react with iodide. I have to predict what the formulas are going to be. I've got K plus 1 and NO3 minus 1. When I use the crisscross method, I'm going to get KNO3. I can do the same thing for lead 2 plus and iodide minus. I'm going to take the 2 from the 2 plus of lead. I'm going to make that the subscript of iodine. I can do the same thing with the -1 charge of iodide, make it the subscript for lead. And you should come up with PbI2. I'm going to clean this up a little bit over here. There we go. All right, let's get this balanced. I see 1 lead, 1 nitrate, 1 potassium on both sides. Oh, I've got 2 iodine on my product side. I need 2 on my reactants. That takes care of that. So I've got 2 Ks now. If I put a coefficient of 2 in front of KNO3, I balance for potassium, and my nitrates are balanced as well. Finally, I need to get back to table F and predict which of these 2 products, if either of them, KNO3 and PbI2, are going to be aqueous and which one will be solid. So I know that potassium is a group 1 metal, so there are no exceptions. Compounds containing group 1 metals are always soluble. I can double check the anion just to make sure. Nitrates also always soluble, so it looks like KNO3 is going to be aqueous. I want to check lead iodide. I'm not guaranteed to have a reaction between these two compounds. I usually start by looking for the anion just because there are more anions listed. So if I find I2, or I should just say iodide, excuse me, iodide is a halide. Halides are generally soluble unless they're combined with silver plus, lead 2 plus, or dimercury 2 plus. Well, it's combined with lead. So that is going to be my solid. So this is a lot of work to take care of one problem. Start off by dissociating. So call that number 1. Step 2 is the recombination step. Step 3 is predicting your products. Step 4 is balancing. And step 5 is predicting which of the two products, if either, are solid. So this is a whole lot of work to get through, and you really want to take your time. Let's do a practice problem together. So here we've got a handful of double replacement reactions to work with, and I'm going to take a little bit more complicated one to walk through with you. Let's look at question number 5. Question number 5, we've got potassium sulfate and calcium chromate reacting. So I'm going to break them up into ions. That's always the first step. I'm going to make potassium ions, sulfate ions, calcium ions, and chromate ions. The tricky part is figuring out what their charges are going to be. Remember, you can use the reverse crisscross method, but you also want to use your reference table to double check and make sure that you are assigning possible charges and that you're not making silly mistakes. So if I look at the reference table, I know that sulfate as a polyatomic ion has a charge of 2-. I know that potassium as a group 1 metal will have a charge of +1. Calcium chromate. If you just look only at subscripts, you are probably going to end up thinking that calcium has a +1 and chromate has a -1 charge because there are no additional subscripts. That is inaccurate. Calcium is +2. Chromate is -2. The subscripts have reduced down or simplified to lowest terms. Be careful, take the time to check the reference table. Up next, I need to recombine ions. So I'm going to take my opposite cation and anions, and I'll pair them up. Let's do calcium sulfate first for no particular reason. Calcium is 2+, sulfate is 2-. So I end up with CaSO4. The +2 and -2 cancel out. For potassium chromate, I'm going to crisscross the charges, and I'll end up with K2CrO4. So those are my two products. Check and see if we need to do anything to balance it. As I look at it, it looks like we're all set with coefficients of 1. I'm going to write them in there, but of course if there's no coefficient in front of the species, in this case the compound, it is implied that the coefficient is 1. And finally, I want to use table F to predict solubility. Calcium sulfates. Sulfates are generally soluble, however calcium is one of the exceptions. Calcium sulfate is a solid, and I think the instructions up here tell you just to put a box around the insoluble compound. I'll double check potassium chromate just to make sure. Group 1 metals are always soluble, and chromates are usually insoluble, so we'd end up with a slightly soluble compound here, and most likely it is not going to precipitate out since we have calcium sulfate doing that. Just kind of one tip, if when you get to the point where you're trying to balance your equation, no matter what you do, it doesn't seem to balance, that is a surefire sign that you have predicted your products incorrectly. Most of the time it just comes down to either not getting the correct charges, kind of doing something silly, like just making this calcium plus and chromate minus, instead of recognizing that the subscripts have reduced to lowest terms. But if it doesn't balance, that's most likely where your mistake is. So go back and repredict the products. I know I haven't given you a ton of practice problems to work on here. You can always Google search and find more, but I definitely tackle these 4. You know I'm going to ask you to do this on your upcoming test. All right, I think that's all I've got for today. I hope this was helpful, and thanks for tuning in.